I'm very honored to be here because I'm kind of a user of Modelica. I met Hilding sometime 1994. I got the first Daimler license on a floppy disk. I think it was version 2.4 or something. But I've never really contributed to the neither the Modelica, Daimler nor Modelica language. But I'm a big fan and a user. And now I'm at Chalmers again, but I started there and then I was at Volvo Cars doing vehicle dynamics, and now I'm back. About the same story Mats has, also coming from Volvo Cars, but very much later. You were at Volvo Cars just a year ago at autonomous driving. Peter is at Volvo Trucks, but we are all with vehicle dynamics, and automated driving is a big part of this topic or this area at the moment. Right. Automated driving, this can be a lot of things really. In figure A, there is a goods transportation. Figure B is person transportation. These are really different purposes with this. Figure 2 shows something related. It's more of a remote driving, which you probably can see already today, but you can think of kind of helping also driver that is outside the vehicle. And to sort out this, there is a lot of different levels, or not a lot, it's 6, 0 to 5, defined by Society of Automotive Engineering. Just to not confuse everything up, we could actually say that the very first vehicles are already mass-produced today, and there are vehicles with something called ACC and LKA, Adaptive Cruise Control, where you don't need to use the pedals, and lane keeping aid, where you don't need to use the steering wheel. And I would say it fits under level 1. But if you have the same at the same time, you actually move to one level up. Because if you can release both, it's quite a different story to take responsibility to launch this kind of function, because then the driver gets in a quite different mode. Much higher risk of him being misusing the system. I would say that the two examples, A and B, up there, they are more somewhere here. The first one is a tractor without a cabin, obviously no driver at all. Now in B, you see there, I don't see a driver, it doesn't seem to be a steering wheel at all. But it's, I don't know exactly how to differ between level 4 and 5. I think there can be different definitions in different days, sort of. Now, we should talk about modeling. But before coming to it, we start with this, which we will use as background many places. And this could probably be done in SysML, I think. But I used PowerPoint instead. Because it kind of, this is a function architecture, and it's really just a way to reason about how to organize the work. But still, it's very useful. This red arrows is some kind of request flow. And to handle this with automatic driving, we could see, okay, we need an input from the environment. And we probably also need an input from human driver, unless we are really on the highest level of automation. The highest level route management, you need to plan the route on that level. Traffic situation management is more of a couple of 100 meters, changing lane, something like that. Vehicle motion management is more like 10 meters ahead, a couple of seconds. And then motion support devices is a strange name for something which we probably would call actuators. So for instance, a driveline can appear as one of the motion support devices. And we need models for all this. Yeah, we can say that the traffic situation management, which Peter will focus on, is instead of the driver handling these situations. The vehicle motion management is needed both if we have automated or manual driving. Right. Yes. So there is some kind of idea what are you actually requesting. So typically simplified velocities, accelerations, and down here it's wheel torques, for instance, or axle steering angles. It can also be engine torque or wheel torque from brake. That means just one part of the wheel torque, because the propulsion would not be in. Right, and beside the blue one here, you need, in parallel with the request flow, you always need some kind of status or capabilities, but you can also feedback estimates, and not the least important is the confidence level of them. Mats will talk about that. Yes, as I promised, I keep this as a background, and then something about models. And again, talking about physical models and data-driven models. As was mentioned, we need both of them. I would say on this level, you look at velocity, energy levels, and so on, and definitely you can find, I think you can, in many cases, you can find physical models here. For traffic situation management, this is so-called one-track model. So this is a tractor, a semi-trailer, and semi-trailer after that. And you can definitely use Newton's findings from 1600s. You don't need machine learning for that. Also here, you can manage far with physical modeling, but you need a little bit more advanced models. And I would say down here, you can, here I picked from a Modelica library. Here is I don't know, remember what, I think it was a brake system. But then we should also envision that, well, for, yes, as mentioned, camera vision and so on, there definitely we need some of the yellow models also. And also in the other areas we can find, for instance, on the route management, we might need macro traffic models, which I would say is more of a data-driven model. On this level, we might need models of other drivers, what is happening in the other cars around us, and what is, and then the micro traffic models. They can also be data-driven. On this side, on the last one here, I take estimators as an example of data-driven. So I think that's, so the conclusion is that we can't say that we need one or the other, but we need to utilize them smart. And here is our disposition, because now Peter will talk about Peter, Mats, and then I will come back in the end. Right?
Okay. Do you hear me?
Yes.
You muted, perhaps. Okay, good morning. My name is Peter Nilsson. Work at the Vehicle Automation Division at Volvo Trucks. Yes, maybe that's a better starting page. I will talk about traffic situation management, or TSM, and I will focus a little bit on trajectory planning and hopefully some comments on the coupling to modeling. First, some repetition. So TSM, what is that? As Bengt mentioned, so TSM is strongly connected to the software representing the virtual driver. So in a highly automated vehicle, the TSM software actually needs to to do the actions that the human driver normally do during driving. I will go through, just briefly, some of the TSM areas, software areas, and I will give some examples of challenges connected to them. Very often you talk about behavior planning or tactical decision. I like to see this as the co-driver. So this is software connected to the person who's sitting next to you and give you high-level driving instructions. So this could be instructions such as keep current lane, make a lane change to left, make a lane change to right, increase the speed, and so forth. So it's not any details in the driving trajectories, so it's more a high-level driving instructions. There are a lot of challenges connected to this type of software. One of them is, of course, the predictions of the surrounding traffic and their use. Sensor imperfection and sensor occlusions. We need to find computationally efficient methods. It happens to be very demanding most often. The behavior that we generate needs to be consistent and predictable. And of course, we need to know what type of situation we're in. What type of driving instructions should we give? So once we have these high-level driving instructions, we can talk about motion planning or trajectory planning. So this is more the detailed level of driving instructions, we can say. So here we also have a challenge of predictions of surrounding traffic. The trajectories we generate needs to be collision-free. They need to be predictable, and in some cases, they also need to be comfortable if the human driver is still in the loop. And also, they need to be dynamically feasible. And often when you talk about TSM software, we often see longitudinal and lateral control. And of course, the controller needs to be robust. Our vehicles are exposed to a lot of disturbances. So we have wind loads, we have a lot of different road loads. We need to handle transition between different driving modes, etc. So this is just a brief overview of the TSM area and the TSM challenges. I will focus now a little bit more on the motion planning and trajectory planning. So what is trajectory planning? So one way to express it is to say that trajectory planning is a generalization of path planning involved with planning the state evolution in time while satisfying given constraints on states and actuation. There is an example of trajectory planning in the right picture. So here you see a tractor semi-trailer combination doing two 90-degree left turns. And you can see, so the tractor is the green box and the trailer is the black box. So you can see that the tractor needs to keep out in order to handle the motion constraints that has been set up in this problem. So the motion constraints are represented in the dashed lines. Sorry. So there exists a lot of different methodologies for trajectory planning. Some of them are connected to numerical optimization. There is a wide range of graph search methods, and there also exist neural network-based methods. So when it comes to articulated heavy vehicles, there are some specific motion constraints that we need to consider. I will try to illustrate this with two examples. So in the top picture, you see a low-speed cornering case. So here you can see that the front unit of the vehicle is not following the same path as the rear unit. So this is the off-tracking effect. And of course, this is very interesting if you're doing trajectory planning for this type of vehicle, that you keep track of what area is not available during driving. There is also effects in high speed. So in the bottom picture, you see a high-speed lane change. So here we can have dynamic amplifications through the vehicle units. So in the bottom graph, you see the acceleration, the lateral acceleration of the first unit and the last unit of the vehicle. So the gray line represents the last unit, and you can see that you have an amplification effect here. And this is really important for heavy vehicles because we can have a very low rollover threshold because we have a very high center of gravity. One way to handle this motion constraints are, of course, to use physical modeling. So one very common model in the TSM area and within trajectory planning is to use the one-track model. So to the right, you can see an A-double combination. It consists of a tractor unit, a trailer, a dolly, and then a second semi-trailer. And you can see the schematic picture of the one-track model below. So this type of model, in this specific example, includes 9 different states. So we have 3 states for the first unit, and then you have additionally 2 for each added unit. Yes, and finally, another very important aspect when we choose methodology for example, trajectory planning for heavy vehicles is the variant combinatorics. So we have a huge amount of different variants of trucks. When it comes to powertrain, we have a 10 to the power 2 variants. Chassis could be 10 to the power 3 variants, and this could be such things as number of axles, distance between axles, number of steered axles, number of driven axles, and so forth. We also have a huge difference when it comes to vehicle load. So the load can vary between 7 and 120 ton, including different center of gravity. And as we have seen before, we also have a variation in number of vehicle units. Most normally we have 1 to 4. So this is also something that we need to consider when choosing methodology for trajectory planning, that it needs to be robust and scalable with respect to variant combinatorics. Okay, thank you. I think that was my short introduction of the TSM area and the coupling to modeling.
Mats Jonasson from Chalmers, senior researcher. So Peter, he has talked about traffic management situation, and that is about planning the motion. The next software that is below is vehicle motion management. And that is the software and layer that is responsible for executing the demand from the traffic situation management. So the challenges for vehicle motion management could be divided into 4 different groups. One is how the lateral and longitudinal control is done. For example, is it good low motion sickness? The second part is associated to fault-tolerant control. For example, could the system provide a fault-tolerant system? Development process is another challenge, mostly system safety. And another one is vehicle motion state estimation that I will talk to today. And I will talk about road condition estimation, and in particular road friction estimation. That is very important. And the reason is that there are many accidents due to slippery road condition. More than 10% of all accidents occurs because of slippery conditions, and many people die. So what is friction? Well, friction is associated to grip. And here we see an example of high friction and low friction. And we have slip and force. So the peak force is the product between friction and normal load. And in order to be able to estimate friction, you need typically to come up to the nonlinear part of the tire characteristics. The problem, however, is that all normal driving is done here in the linear part. And there is the same characteristics independent on friction. So as long as vehicles are driven here, it's not possible to estimate friction as long as the tire is used as a sensor. And that is a particular problem for self-driving vehicles, because they are planned to move without large accelerations and so on. So we're talking about low friction and mid friction, high friction. So normally for safe-driving vehicles, the friction should be more than 0.4, otherwise it's too slippery. So we're trying to capture the problems with friction. Why is it so important? We can look at this confusion matrix, where we have on the x-axis the true friction we have. Low, for example, snow, or high, for example, dry asphalt. And on this y-axis we have the assumed friction, the friction we think that we have. And as long as we think that the friction is the same as it's the true friction is, then it's easily, we can adapt the speed to the road condition. But if we think that friction is low, but in practice it's high, then we will get false warnings. And another problem is that if we should adapt to low friction then, because we think it's low friction, then the vehicle will drive very slowly, and it will not be efficient. And the opposite situation is if we think that friction is high, but in practice it's low, we will drive too fast then, and there will be a lot of accidents. Okay, so how can we estimate friction? One way is to use an optical device and then have some sort of map from texture to friction. But what I will talk about that is these two methods, where the tire itself is used as a sensor. So one way is to use model-based estimators. That requires that we have relatively good knowledge of the tire physics. We can also apply machine learning. So then we don't need any knowledge about the physics any longer, but we need a lot of training. So this is a typical example of how friction is estimated by a model-based design. First, it's pre-processing using wheel speed sensors and inertial measurement system and a steering angle sensor. And by using physical model, both kinetic and kinematic models, tire forces and tire slip could be estimated. And then by using a filter and a model-based design, friction here can be estimated. So this here, what we can see here is measured data. So this is a model for low friction, high friction. And as you see here for driving close to zero, it's impossible to say if it's low or high friction. So this is a project at Volvo Cars where they attacked the friction estimation problem by machine learning. So that they had access to more than 100,000 kilometers of data. Also annotated data, so there have been sitting people and manually noted if it's high or low friction. So to see here is what they call features, that is up to 86 different signals that was logged in the vehicle. For example, GPS, temperature, wheel speeds, and so on. And what we have here is the correlation to friction for all these 100,000 kilometers of data. So from that study, it was obvious that the temperature had a large correlation to friction, GPS and wheel speeds, and also this metadata that was manually annotated in the vehicle. So of course, temperature is obvious that it could be related to if it's snow or ice and so on. Later on in this project, the engineers understood that, okay, GPS, that is because the training was done in the north part of Sweden or in Gothenburg. So in principle, if you know where you have recorded the data, of course you can understand if it's low or high friction. And this result here that the type of road and the surface was important and correlated to friction was some sort of indicator that there is a need for another sensor, namely a camera or so, that can be used to detect what type of road we have there. So Trying to summarize the challenges is that it's during normal driving very hard to estimate friction independently of machine learning or physical-based modeling. For the model-based, it's hard to model the physics. There are so many types of tires with different parameters. And pre-processing is very hard to do exactly. For machine learning, it's hard to have a generalization of the algorithm to adapt to different situations and different markets. And it would require extremely large testing that is maybe not possible to do. And finally, that training also need ground truth to another extent. So it's also hard to measure friction. Yeah, Bengt.
Right. Hello again. So I will sum this up by going back to this picture again. And when we say virtual verification in automotive, it more or less means simulation. And that is, we verify functions by simulation instead of verify them with a real test vehicle. So what we need is, of course, we need typically a model or something that represents the control things here, but we also need a lot of other things. We need models of the mechatronic actuator. We need wheels, tires, suspension, and body. And all this is for the subject vehicle, the vehicle that we are designing, the ego vehicle. But then this vehicle position itself into an environment where we have models of the surrounding vehicles, and from that we, in some way, we should sense where we are. So this is the whole loop for virtual verification. And I would say that when you look at the models used for control design up here, and then look what do you need for corresponding. I mean, the motion up here is represented down here with a similar model. And I would say that in this part, the yellow part, you need kind of higher accuracy, and also good if you have a higher validity range. Because when you use the models for control design, you know approximately you can, for instance, swap models between different high and low speed area and so on. But I think so this is kind of more difficult, but what maybe makes it less difficult is kind of it only needs to be simulatable. You don't need to be able to invert them, linearize them, and so on. Right, here's one view. I think I was writing maybe my view. No, I changed to one view. But this is my view of model-based engineering. Starting from that we have something to solve and we have a final design. And in some way we loop, and we can use real-world testing, building a prototype every time. But of course we can also move over to the theoretical world and do, I would say that the virtual verification step is up here, or the simulation. It's important to be able to do the numerical simulation and also to interpret what is valid, how does it actually going down here. And here are terms which I use. Well, I show them like this. I think that Modelica, I call them mathematical model because I place them between physical modeling, where we actually do the physical assumptions. It's often just a drawing, free body diagram. And this is more of a concrete equations. Then sometimes we also need to go via an ODE formulation. But of course, with Modelica tools, we can jump that. It's kind of automated from here all the way to simulation result. Actually, one more thing. The most important thing in this picture is these dashed boxes here. Because for automotive, there are so many requirements and so many subsystems. So it kind of explodes in complexity just because we have so many different subsystems, which we can handle with co-simulation, and we have so many requirements, meaning different maneuvers to run, which we have to handle in some other way. Okay, then I pick a wheel model as an example. And again, here's one of these long track combinations Peter was into. And the motivation really to this is that they produce easily 20% less carbon dioxide. But the problem is that they have so many wheels. So in this case, if we count the axles multiplied by 2, we get 26 wheels. Many of these are also twin-mounted tires, so it's probably 50 tires on this machine. And we want to have this as a building block, a tire model. And I started here to kind of draft the physical model, I would say, because I start to introduce the different physical variables. And some use cases here where it becomes difficult. There are basically two things. One is when you look at the longitudinal vehicle, control of the translational, and look at functions like hill hold, adaptive cruise control, and so on, you should be able to stop, maybe reverse, fully stop, going up and down the hills. Another challenge is this one. If you start to turn, you get forces in at least two directions in the contact patch. So you want to reuse this model. And if your package is a bit more Modelica-like, I would say, but it's still not Modelica, but in my world, it's approaches here. You recognize the wheel itself, the physical quantities, but we add here actually the brake disc, because the brake is so much integrated in each wheel, so it's probably practical to have this as a part of the wheel module. And then we also have the very close to wheel control of the brake actuator could very well be mapped into a mechatronic wheel model. But then there are difficulties with the mechanical part of the wheel. Trying to give them a picture, I made like this. Well, basically, the wheel is balanced between two drive friction contacts. One is the brake disc, which is relatively easy. The other one is the contact patch with the ground, which is not very easy. So, and also I would like to have some equations. So here is a typical concept for a tire model. Omega is the rotational speed, and it appears in the denominator, so this is a problem. When you start to look up the wheel, everything gets singular. Another singularity is this one, indicated by these two force arrows. And I underline down here, because to get the direction of the friction force, we need to rely on that the lateral speed and the longitudinal sliding speed, they can't be close to zero, because if both are close to zero, we try to look at the direction of a zero vector, and it doesn't work. It's singular. These two are very similar. This is the brake disc, and this is the rolling resistance. Rolling resistance is kind of well established, accepted that it's counter-directed to rotational speed. So I would say here we have some kind of signum of speed. And finally, we have this problem that we have more than one wheel. And if you should be able to stop this and lock some of the wheels, you will get static undetermined system. So you really need to handle different problems in this. But assuming we can do that, we should try to see how it ties together in this one. Like that. Yeah. So this is the one, the mechatronic wheel module. So maybe there are 26 of these. They should hang like here in the total simulation loop. So we need a stable mechatronic wheel module if we really should be able to handle stop still, stand still, reverse, etc. I think that was all from my. So I just have I think 1 or 2 slides. Yeah, you have seen. This is Peter's long combination, Mats friction estimation, and the wheel model. And definitely automated driving needs modeling in many aspects. Traffic situation management, vehicle motion control needs physical model. Virtual verification drives that we need really physical models. And it also includes exchange of models because we need to do co-simulation. Or just trying to place a seed here. Could we do something like co-modeling? We say co-simulation, indicating that we use FMI typically. Would it be possible to do co-modeling? How far is that to be able to kind of combine the IEs? I think that would be helpful with all these 26 wheels. References. Thank you.